Hello. Today I will be explaining the interesting physics behind the throws of one of the greatest sports there is, ultimate Frisbee. To understand how and why these throws move in the directions they do, one must look at a Frisbee as an object moving through a liquid. This branch of physics used to calculate momentum is called fluid dynamics. Objects moving through air can be categorized within this branch of physics because air is a fluid and follows many of the same principles that thicker fluids, such as water, follow. For example, objects underwater with a flat aerodynamic shape, such as fins, are used to steer huge ships using these same principles. Similarly, wings and fins on a plane are used for stabilization and steering. A Frisbee follows many of the same rules. In a normal air environment without any extra wind or excessive humidity, the behaviors of a Frisbee may even be predictable. To predict movements of such complicated motions in fluid dynamics, physics use complex equations called Navier-Stokes equations. These equations provide a list of input variables in order to predict object, or in this case Frisbee, motion. These equations provide relationships between the pressure, temperature, and density of a moving fluid such as air. The specific equation being demonstrated in this video is particular of incompressible flow. Incompressible flow means that the density of the fluid remains constant and that the fluid is uniform in all ways. The first term in this equation is the partial derivative of u, which is the variable for flow velocity, or how fast the fluid is moving. The second term, introduced has both flow velocity and the divergence, represented by the nabla symbol. Divergence is a quantity found in vector calculus, but we won't go too far into that. Combined, these first two terms create the inertia, or resistance to change in motion, of the fluid. The next term adds v, which represents the kinematic viscosity, or how thick or thin the fluid is, to the equation. On the other side of the equal sign, we have another new variable, the w, which represents thermodynamic work. This is the energy a system transfers to its surroundings, so like giving off heat or something like that. Finally, the g represents any forces not included within the rest of the equation. This would be gravity in our example. This equation, although quite complicated, explains the processes of the Frisbee's flight and can help us predict what will happen after we throw the disc. Next, I will demonstrate some abnormal throws that help to show the fluid dynamics acting upon the Frisbee. Keep in mind, in an environment without air, the fluid dynamics, the Frisbee would never change direction because there's no force except gravity being acted upon it. The first throw I will demonstrate has no specific name, but is a common side effect of many throws when executed at a specific angle. The disc will move away from the line between the thrower and the catcher, but then return towards the catcher. This is very useful in ultimate games because it can allow the disc to curve around the defenders and still make it to the desired location. Additionally, those who did not view the beginning of the throw would only be able to guess at where it is headed. When at an angle like the one shown in this throw, the Frisbee can cut through the air. This creates a curving path. Gravity pulls down on the disc, but the shape and tilt make the disc slide through the air at an angle. This effect is exaggerated when the disc is thrown in a special upside-down way. Next, I will demonstrate another seemingly impossible throw. This throw is known by the ECS Ultimate Squad as the ground skipper or lawnmower because of how it moves along the ground. The throw is sometimes used in-game to go under a defender's reach and still be able to connect with the target. A regular backhand throw is released with an upward angle but forced to the ground. The disc travels downward but eventually makes a magical turn back into the air. The angle of the disc once again beckons the disc to continue upward. When the disc is carefully thrown, it can overtake the initial downward motion. The fluid dynamics help make this improbable change in direction possible. The final throw I will demonstrate is entirely a trick throw that is completely useless in game. The throw is used occasionally by players at ECS when they seem to be the only capable player on their team. While this throw has no official name, it could be referred to as the boomerang throw. The disc is thrown at a very sharp angle into the air in front of the thrower and catcher. When the disc has reached its maximum height, it returns in a path remarkably similar to the original throwing path. With a perfect throw, the disc can be thrown and caught by the player without much movement. The angle of the disc upon release is so severe that it continues to increase until it becomes close to 90 degrees. Once at the top, the disc is still slightly tilted, so the fluid dynamics take over and cause the disc to return on a similar path. This is a truly incredible phenomenon to view. Thank you for watching the video, and I hope that you learned something about fluid dynamics, and perhaps you will appreciate it a little more when you see someone throwing a Frisbee. Thanks again. Goodbye.